We have a great speaker, actually a return speaker, because Zach spoke last year as well. He's back again and he's going to be speaking about fuzzing the EBPF subsystem. So big round of applause for Zach.
Hello. Oh, audios are working. I love the backstage people so much. Cool. Hello. Fuzzing the EBPF subsystem. I will add bracket of the Linux kernel. When I submitted this talk, it was the Linux kernel track. I'm like, oh, wonderful, made just for me. I actually paid one of the InfoSec people a large sum of money to get that track created. That's not a joke. And then actually now I'm on main stage and people don't know what the subsystem is of. It's of the Linux kernel. And I'm Zach, if I'm to be believed. I have animations between these slides? Okay. That wasn't meant to happen. Who am I? Most unimportant part of the talk. I'm Zach. I'm a final year computer science student at UNSW. Finally going to escape there. Part of Security Society, or SecSoc, the Cybersecurity Society there. Play CTS with Emu Exploit sometimes, and occasionally I am found at Australian conferences where people listen to me ramble. Now to the more important question, what's EBPF? It's a subsystem of the Linux kernel, as you might already know from 30 seconds ago, but basically we can submit arbitrary programs to be run at various hook points throughout the kernel. And the way I like to think of it is kind of just an alternative to Linux kernel modules, because Linux kernel modules are like kind of brilliant but also kind of really, really terrible, because like they're written in C, and C is amazing because you have memory corruption and also a compiler that kind of just lets you do whatever you want, even if you shouldn't do that. And so you get these people that write really bad Linux kernel modules and then compile them, and then, you know, they're found in a bunch of systems and really vulnerable and terrible. And also the other annoying thing is like you have to be root to load kernel modules, because otherwise like how could you have a non-root user modify kernel behavior? That's fundamentally unsafe, like kind of. But the thing is that EBPF ideally will allow any user to submit a program, and this is a program that is being run in the kernel context. So that sounds very whack. In actuality, it depends on capabilities, because they quickly realized it was a very bad idea to let everyone submit these programs. And as you can see here, can't see my mouse, or can see my mouse, there's 10 million different program types. And yeah, you might be thinking hook points, ooh, buzzword man, tell me what that is. But yeah, so the sort of original BPF was mostly for networking, and that's what I'm most familiar with. So it's like accept or rejecting an incoming packet, handling a packet that's been specifically rerouted, but it's now much more flexible. You can mess with, say, file system operations, or there's even things like these options called kprobe and uprobe, which allow you to kind of have custom hook points, and people do like crazy stuff with that. And yeah, as I just said, we're kind of allegedly letting any users run kernel code, so like how does that not break the entire security model of the Linux kernel? And that's because these programs must be verified for security properties by the verifier. And so the verifier asks questions like, is it memory unsafe? Are we handling uninitialized values properly? Will the program terminate? And it rejects any programs it thinks might be unsafe. It's conservative here. We can't accept a program where we're like might be unsafe, but we're fine with that. It's like, no, we have to be 100% confident it's safe here. And so initially, yeah, we just let everyone submit EBPF programs because the verifier is perfect, because we say it's perfect. But then people kind of saw this and got curious, and unfortunately the verifier is not magic. It has bugs in it, and if the verifier has a bug in which it incorrectly accepts unsafe programs, cool, you now have kernel code execution doing stuff that it shouldn't be doing. The process of submitting this stuff is, yeah, you call the BPF syscall, and yeah, it goes verifier, which will either reject you or approve you. And then this one specifically says JIT compiler. Technically there is both a BPF JIT compiler and emulator, which you can toggle between. But honestly it tends to not affect stuff too much, insofar as that, you know, if a bug is in the verifier, you can probably go at it with either the JIT compiled version or the emulated version. So that's what eBPF. You might be thinking, why target eBPF? And first I'm going to say why not to target. And I will say, like, from a business money perspective, I think this is a terrible target. It used to be nice because it was exposed to unprivileged users, but those days are gone for like a year or two now. And now you need either cap BPF, which is honestly I've never seen in my life, or you can have other higher privileged capabilities such as cap netadmin if you're doing like networking eBPF, or say cap performance monitor if you're doing that sort of stuff. And so you can get a slight privilege escalation to root from these. There's also SE Linux. I won't lie, I don't know how SE Linux works. I remember reading old papers about like disabling it with kernel code execution, but I don't know what guarantees it gives you these days and how that fits in with the kernel. So maybe you can mess with that. Of course, if they like explicitly opt into unprivileged eBPF, then you do have full LPE, but that's kind of rare. You kind of have to be stupid or like in a very weird situation to enable that. Apologies if you have that enabled. So why did I target it? I don't just choose bad targets and suffer. I think it's an interesting target. So I wrote a fuzzer which pretty much automatically generates test cases, and so different programs have like different sort of formats to their inputs, and some of them are really boring, but eBPF, you are submitting programs for it to run, which means my fuzzer needs to generate programs from scratch. I'm like, that seems cool to like my nerd self. Also, it just seemed under-researched in my opinion. There is syscaller, which is the most popular Linux kernel fuzzer, and it sort of tries to fuzz all of the system calls, and for that it defines its own sort of language so that you can define grammars to describe the format of those system calls. And for example, open, I assume people know what the open system call is, returns an integer, like strictly type speaking, but that integer represents a file descriptor. And so syscaller will make that the file descriptor type. And so when you call read in syscaller, it will ask for a file descriptor and not an int. And this is cool and all for like that basic example, but when you get to such complex types as an eBPF program, it sort of falls apart. And so it doesn't do a good job, which is good for me, because otherwise there would be no bugs here. And then I looked at specialized fuzzers, and there's just not too many of them. Yeah, there's like one that was a decade old, framework published by Google. I think there was one which I did see which seemed cool, but then found like one bug and they're like, called it a day. They're like, I've proved that my theory works. And then I saw a good academic paper recently, like 2 weeks ago. So like, yeah, there's basically nothing. And so I'm like, okay, well if people aren't taking a poke at it, I can probably take a poke at it and find a bunch of bugs. And also, yeah, I just think the sort of bugs you get from the verifier are interesting because they're logic bugs about analyzing program properties, which sounds fancy. But what I mean is like, if you get like an out of bounds write into the heap, I'm like, okay, well I've seen this before. I'm going to go find an elastic object and tinker with it. Whereas like each eBPF bug, I'm like, okay, well how do I use this like to craft a program which exhibits like behavior, which I turn into stronger primitives. So I just thought it was cool. And so that's about eBPF. Let's introduce the fuzzer, which I have called FFEBPFF, which stands for Freaking Fabulous Extended Berkeley Packet Filter Fuzzer. It's full name. And I originally had a section talking about like infrastructure, how I set it up, but I won't lie, I did just steal syscaller's notes. So go read about how that does it for a better summary, and I'm mainly going to talk about generating inputs, because the main reason why eBPF is interesting is that the inputs are weird. Cool. Before I talk about how I generate them, you sort of need to know the structure. And we are submitting eBPF programs. And an eBPF program is pretty much just an array of eBPF instructions. Like, it's very simple. Here is the actual structure we use when doing the system call, and it's literally .instance is the instruction array, and we tell them how many. So like, we don't have like an actual file format or anything. These eBPF instructions form a minimal risk instruction set because it was designed from the ground up. Wouldn't want to verify a CISC instruction set because imagine having to think about the security properties of vector compare, keyword, swap, exchange. It's like, I don't want to think about that. So keep it as simple as possible. And yeah, verifier checks if the program is safe, but also if it's syntactically sane to begin with. One last thing is, how do we communicate from user land to kernel land? Because one of the main things about eBPF is, like, say people love collecting performance metrics with it. And so we do that with things called eBPF maps. They're just different data structures like arrays or hash maps, and once again we make a syscall saying we want to register a map, and it gives us back a map FD, which we can use in our program to talk, and then we can look at it ourselves with more system calls. Now, you don't need to ponder all of this, I just wanted the slide to not look empty, but the eBPF instruction format is this, and it is 8 bytes total. We have an opcode, a destination register, source register, offset, and immediate, and it's, yeah, pretty simple, thankfully not like a variable length instruction set. The opcode has 8 different classes, of which we have effectively memory operations, ALU operations, and control flow, so like branching and jumps. We're going to stay at a relatively high level view of these things, so I am not going to be educating you on the difference between BPF load instructions and BPF load X instructions. Cool. Now that I've explained the format, how do we generate them? And at the start, I take on the very nuanced approach of doing cat/dev/urandom. It's never been done before. So unsurprisingly, or maybe surprisingly to some, this wasn't very successful. You mainly do that to see, cool, your fuzzer's alive, it's not immediately crashing and stuff is sane. But the other reason this is actually nice to do for BPF is the verifier log. Basically, you know, for the user experience, for like developers, if they are submitting programs that they want to do for real work, and imagine those programs get rejected. It's like, well, why did that program get rejected? You either have to like look really hard at your source code, or you'd have to start trawling through like Linux kernel code for hours, which I don't recommend. And so obviously this was like a design problem to eBPF. So they're like, okay, when we are analyzing the program, the verifier is going to construct a log, and if it gets rejected, it will give you that log. And this log's like incredibly verbose. It's like, hey, for every instruction ever, had the entire stack state and register state and, you know, the weather for the day. But thankfully, it's pretty easy to minimize because at the very end, it's like, oh, you tried to dereference a null pointer. And so I would run this for like 10,000 iterations and then just chart how many programs are getting rejected for what reasons. And as I mentioned, verifier, before it talks about semantics and safety, it talks about syntax. And so I kept getting these things like invalid opcodes, but the verifier is being like, what are you even giving me? These aren't valid instructions. How can I execute them if these aren't in the instruction set? And as I mentioned, the opcode is officially just a U8. But for U8s as a type, I can just say generate me a random one, but once again, they might not be valid, such as the opcode F2. And so U8 as a type doesn't properly encapsulate the opcodes. I programmed my fuzzer in Rust. I will shill it hopefully only a tiny bit. And so I modified this as an enum. So you can have, you know, all the fields here, loads, stores, ALUs, and jumps. And then we have to technically model a bit more here. But now sort of we can make use of having like a decent type system to make it pretty much impossible to construct invalid opcodes, because if every single enum variant correlates to a valid instruction, how are you going to make an invalid instruction? And then you can say, instead of give me a random U8, give me a random EBPF instant class, and we're happy. Technically it's not impossible, but I'll mention that later. And there's more invariants. There's too many. The other one that I think is sort of, I guess, relevant to talk about is we have the instruction source mode. So when we have an instruction, it will either be using the source register or the immediate field, and never both. I don't want to say that confidently. It's a weird thing, actually. So if we're in immediate mode, we're like, okay, well, we need to set source register field to R0, and similarly, if we're in register mode, we need the immediate field to be 0. Otherwise, we get more complaints. And yeah, there's just so many of these like different invariants to make sure that we're sort of syntactically, like, eBPF is happy with us. Things like aligned memory accesses. If we're doing bit shifting, we don't want to shift more than 63 in a 64-bit system. And like, I don't want to run through all of these because like, we don't handle them all in a particularly novel manner. Where possible, like, make use of types to represent the sort of grammar of the thing you're fuzzing. That way, at a value level, you can't have invalid like grammars or like values. But like, if that's not possible and is not always possible, sort of just enjoy using safe constructors which sort of do all the checks and then output the resultant instruction, and I can rely on it being syntactically valid. Cool. So, types. Already talking about types. Our program, after we obey like the 50 billion different invariants, now makes syntax wire. It's the eBPF verifies like, hey, you sure are giving me instructions. But semantically, which is like what our program's actually doing, still kind of doesn't make sense. Because the fuzzer has no notion of types in the eBPF program. So we're trying to do things like multiply a pointer or load from a scalar. And so we introduce the notion of types for our registers, and it's a pretty simple type system, thankfully. We mainly have 3 types, which is pointer, scalar, or uninitialized. Pointer has associated with it the pointer type, because talking to the stack is different to talking to, say, the packet we're working with, both of which are represented as pointers. Scalars technically have an associated width with them, and uninit is uninitialized. And yeah, this actually gets us very far insofar as this matches the verifier's own type system to like a pretty good degree. Sorry, one thing, I will probably refer to like the, I guess, tuple of like register to associated like type as the like variable state in the future slides. Cool. So now that we have this notion of these basic types, we can now ensure things like our load and stores are now only going to operate on pointers. As the memory location, of course, we can still store scalars or whatever. And same for things like atomic instructions, like comp exchange, which tripped me up. ALU instructions, we can now guarantee will work on scalars because, you know, verifier is strict. We aren't allowed to divide a pointer or whatever. Some like minor exceptions for things like adding or subtracting to a pointer, because then how do you implement arrays in assembly? And uninit values are sort of used in the like opposite manner, in that we kind of never want to ask for an uninitialized value without, because then the verifier is going to be like, what are you doing? But we can do it in the inverse manner of when querying the variable state, say, hey, give me a register any type as long as it is initialized. So the example for that is the move instruction. As long as the source register is initialized, it's fine to move that to the destination register. And it's nice if we magically have these types to query and sort of make sense semantically, but like, how do we know that like this register is this type or so on? Oh, here I mentioned variable state, that should have been earlier. So yeah. basically when we are generating an instruction, it has the variable state and it can make queries to that variable state with different requirements. But it's actually given mutable access to the variable state because the state obviously changes as the program executes. And certain instructions will modify different registers and what their types are. The easiest example is move reg will copy the state of the source register to the dest register, overwriting the pre-existing state of the dest register. And also, load instructions initialize the dest register. What exactly it does depends on where we're loading it from. And yeah, just with that, we have types in our program and can make decent amount of semantic sense to the verifier. And then finally, let me check how long I've been rambling, 20 minutes. We have battling control flow analysis. So, semantically, we kind of have ALU and memory instructions pretty good, but jump instructions still really, like the verifier still really hates us. And that's because I haven't talked about the offset field, which is kind of a niche thing for most of the other, for some of the instructions, but jumps really care about it because the offset field says where we're jumping to. And so we need to reason about our control flow such that it makes sense at an instruction level and also at a program level. Instruction-wise, it's actually kind of easy to reason about. We need to jump inside our program. So if we have a 10 instruction program and we say jump to instruction 20, the verifier is going to say no. So that's the first thing. And also we can't jump into the middle of the instruction. Those of you familiar with like instruction sets and encodings, you're like, hey, the instructions are 8-byte aligned. How can you even jump into the middle of those? Because like the offset will just be a multiple of 8. To the people that thought exactly that, very cool. And that's because we have a single, I kid you not, a single 16-byte instruction to thank for this issue, which annoys me. But onto the harder issues is the program level issues. The first one is that the program must always terminate. Now, I regret to inform you, the verifier did not solve the halting problem. It is up to the submitter to like, the onus is on the submitter to prove to the verifier that their program terminates, and it can be like very reasoned about in a automatic manner. The next thing is that all instructions must be potentially reachable. So if you had an instruction and you always like jumps ahead 5, the like instruction in between might never get reached, and that makes the verifier mad. I think that might be due to either, you know, that's an indicator your compiler is doing something weird, or also because when people were exploiting it, we would purposely leave in dead code, which is always jumped over because we analyzed the program wrong, but we do jump to it and then we're more free in what we can execute. But now it complains about that. And then lastly, we can't break assumptions about the variables types. I didn't know how to phrase this elegantly, but this example, say we load from register R1, indicating it is a pointer, and then we move dead beef into R1, which is a scalar. And then we say jump back to 0. Now if we try to load again, we're loading from a scalar, which is obviously not valid. So we need to make sure we are not breaking our like type system here. So like, how do we go about this? And when I went into this, I just treated programs as an array of instructions, because that's literally kind of what it was. But now I sort of shifted into representing it as a graph of basic blocks. For those of you that don't know what a basic block is, fair, it is a block of instructions in which all of the instructions except the last one are non-branching. And that's nice because you know if you execute the first instruction of that block, you will execute every instruction until the branching instruction. So in a lot of control flow analysis, people talk about basic blocks. Now this graph is going to be connected by directed edges, and those edges are formed by jump instructions. The reason they're directed is obviously if instruction 0 says jump to instruction 5, that doesn't mean instruction 5 has to say jump to instruction 0. So they're directed. And lastly, we do have implicit edges, because obviously most of the branches are conditional. So if I do j equal register equals 5, we will have the edge in which that is true and we jump, and the implicit edge in which that is false and we just continue, which is kind of also a jump. And here's this terrible looking diagram. I don't have any arts people to do this for me. But yes, you say you have index 0, which says jump to 5, so it has our directed edge here. But the implicit edge will go to index 1, which will also say jump to 5, in which we exit. Cool. So now that we've shifted how we're thinking about control flow, let's start targeting the first issue of reachability. We want the graph to be connected, except that's technically a misnomer. We do want stronger guarantees. We want every node to be reachable from the origin node, which is literally the node that has instruction 0 in it, because we always start executing at the first instruction. Kind of, there's weirdness going on, but that's out of scope. And for every node, we want to be able to reach an exit node. So that is talking about having all of our code be reachable and all of it terminate. And yeah, these things are stronger than just connection. The way I did this, the actual algorithm is messy for like a number of reasons, part of which is me not being smarter, but we sort of iteratively add nodes, starting from the like first node, which we always know we want to construct. And when we see that we have the last node, like that we know we're constructing, we do a scan of the program for any unconnected nodes. And because of how the algorithm works, we know that the node we're currently operating on is connected. So we then connect to all the unconnected nodes in a sort of linear sequence, and then that last node then connects to the exit, which allows us to say that the program is connected and all reaches exits. Technically, I think you could be smarter about this and maybe have more sort of general, sort of weirder programs, but this was a way that made sense to me to get these guarantees. Here is an example of a more complex one that is an issue. So we covered this, but say we have index 1 has the implicit edge to 2, which is saying that it's always going to jump back to 0. Now, this graph is connected, but index 3 here, this block, is not reachable from index 0, so like we would never be able to execute it, so we're going to get complaints. And so what I would actually do is if the index 2 block is the last one I was making, I would do this check and I would say, hey, index 3 isn't actually reachable, and so I would instead always jump to it, and then that one immediately exits. And like that, we have these nice guarantees about stuff being reachable and exiting. And then we have block prerequisites. So I talked about not terribly messing up the type system. The way I thought about this was each basic block has a prerequisite variable state. So that sounds fancy. So what that actually means is like the block will be like, hey, I'm going to use register 8 as a pointer and I need register 2 to be in it. And for another basic block, when we're choosing where to jump, we can only jump to another basic block if it satisfies the prerequisites. One thing is that the exit block has no prerequisites, you're just choosing to exit, so you can always choose to do that. I used to have bugs in my program because the blocks would be mad at me after not having anything to jump to because I didn't think of that. And yeah, just a little bit of my code is you have like satisfies prereqs, this is how I'm choosing to represent them in like actual Rust types, and it just says yes or no. And say when we're figuring out what blocks we can jump to, we just iterate over them and filter them according to which ones we can actually satisfy the prereqs for. Cool. The last thing here is that we need to prevent infinite loops. You're like, why do we need to prevent infinite loops? Callback. We want our programs to terminate, and infinite loops don't terminate, in case you didn't know. So cycles are allowed in the graph because I want my programs to be like weird and like to be flexible when I'm generating them. So I want loops in my program. But because of that, the graph representation doesn't help differentiate infinite loops from normal loops. It can just say, yeah, you do have loops, or no, you don't have any. So, to reason about infinite loops, I would need to precisely track the registers, their exact values, and be overly conservative. And what that means is I would just be copying the eBPF verifier and be doing its job. And I don't want to do that because the verifier is kind of big and very complex. So I would either be working from scratch and take forever and add a ton of complexity to my code and make a bunch of bugs, or I could just copy the way eBPF did stuff, but then I would be copying all of the stuff they sort of subtly, implicitly did wrong and not realize it. So I just made the call of like, it's not worth it to tackle this, and didn't. If you can think of an easy way to sort of reason about infinite loops, please tell me. And that is generally how we did inputs. So we have opcodes and invariants, which we need to obey to make sense syntactically. And I recommend capturing as much info about those in the type system to make it impossible to violate at the type level, at the value level, and otherwise using safe constructors to kind of encapsulate those checks. Then we introduce the notion of types for the variable state, which we need for semantics to avoid loading from scalars, multiplying pointers, and more. And each instruction can, of course, query that variable state for registers it can use, or it can update it if it modifies it. And then we have control flow validity, which we model as a graph. I know, amazing for me to come up with that. That's a joke, it's a very common thing. We ensure connectedness, but also actually the stronger guarantees. We ensure the variable state is respected for a block, but infinite loops, I'm a quitter. I didn't know how to tackle them. Definitely room for improvements and stuff I want to do. I want to explicitly pair load and store operations, because if we store then never load, it effectively acts as a no-op. There are these things called EBPF helpers, which are functions you can call in the program. That seems like there's code there, so there's bugs there. But I would need to upgrade my type system like to a notable extent to be able to work with those. And then lastly, using EBPF maps to detect info leaks, where I would register a map and at the end of a program store all the scalars. Then I'll disable KSLR and check all the scalars and check if any of them are actually kernel pointers. Hopefully I'll do these. You can just steal my ideas and do them, but you know, if you do, tell me and I can be interested. And so, 33 minutes, talking about fuzzer design, because I didn't want this to just be about here's how you generate eBPF inputs, because that doesn't generalize too well. So I want people to hopefully be able to take some stuff about fuzzer design in general, and this is, I guess, a bit of a step back. Fair warning, I am not like the most advanced fuzzer person to ever do it, so some of these insights are hopefully helpful, but I'm not saying all of them are going to be particularly novel. It's just stuff that really stood out to me when I did stuff. First off, if you can automate stuff in the development process, I beg of you to do it. I always have this issue where it's like, oh, it's just free commands, I'll just run it now, and then I have to run it every single time. And say I'm fuzzing the kernel, so like with userland, to run the program, you sort of just start the fuzzer, which spawns the process. But for the kernel, I have to compile the binaries and then copy the fuzzer binary and the relevant libraries to the init ramfs folder. And then I write the init script in the ramfs folder according to the options I set. Then I compress it. Then I run ffmanager, which then spawns QEMU, which I'm using to virtualize. So like that isn't too complex, but it's just really cringe to like do all those commands all the time. So yeah, spend as much time, like you want to spend as much time finding bugs and developing exploits and less on all the cringe stuff. So like stuff I did, yeah, running the program, some automatic triaging scripts, generating equivalent C programs for eBPF inputs, because it's nicer to work in C than in Rust for these things, at least when working on just submitting the program, and setting up swapping between different kernel versions. Next, type systems. I've already rambled about them, but statically enforcing things about the program's grammar is wonderful. Like, because that's how the type is defined, values of that type sort of have to obey how the type is structured, so we don't have to worry about violating parts of the grammar. And also, I'm not 200% sure about this, But I think it's also maybe more efficient insofar that if you just have stuff encoded in the type system, it's just obeyed when you're like generating the code. Whereas if you have to dynamically check it, that will be instructions generated to be like, hey, I'm looking at the value and I'm modifying it and so on. Once again, the easiest example to draw on is using the enums to represent the opcodes, to which it's near impossible to construct a value of an enum that's not a valid variant. Say near impossible, like in Rust you can do unsafe mem transmute, but at that point, like if you're complaining you're shooting yourself in the foot, you like went and bought a gun and ammo and loaded the gun and took off the safety and then shot yourself in the foot and then complained, so like it's pretty hard to do. However, type systems aren't magical, or at least too magical. There is a bit of magic. And so sometimes, yeah, you can't encapsulate all the info you want to in types. Once again, bit shifting, I want to be limited to 0 to 63 in the immediate field because I'm in a 64-bit system. So that uses the im field. Other instructions want the im field as a normal U32, but bit shift, it's like, so what do I do here? Do I now have an enum for the im field with bit shift as a U8 and normal as a U32? Because that's kind of a pain, because now I have to match when I'm ever working with the im field. And like a U8 here doesn't even properly restrict to 0 to 63 because it can go up to 255. Zig has support for arbitrary size integers, but like I'm not in that language. So this is just meant to show sometimes you kind of do need to give up on encapsulating as much info into the type system because sometimes it becomes too unwieldy. But when Rust gives me dependent types and lenses, I will be all powerful. Now onto the bad and the stuff I fucked up. So differentiating failures. I will say, please, please, please make sure to clearly differentiate between your fuzzer failing and your target failing. If your system or like your setup crashed, what's happened to you? Like, have you found a real bug, or does the fuzzer have bugs? Or like, yeah. So how much can you trust your fuzzer? Once again, shilling a little bit of Rust, I really like having a strict compiler because you have a stronger like sense of trust on your program. But it's not a silver bullet, of course. We haven't made a programming language that makes you have to think about stuff logically correctly yet. So how did I stuff this up? Yeah, I run the stuff inside QEMU to virtualize it, and in the init script, I run the actual fuzzer program as the final command in the init script. Now, does anyone know what happens when the init script or the process exits? Kernel fucking dies and complains at you. So the kernel panics when my fuzzer like finishes. It's like, yep, I fuzzed 1,000 iterations. I've done my job. And all of my scripts see like, oh, the kernel's like panicked. You found something amazing. And then I like open the file. I'm like, init died. I need to delete this and stuff. So that's an example of me not differentiating between my fuzzer like exiting and being normal and like how I want to capture bugs. So think about how you're going to do this. And yeah, here it is. Attempted to kill init. I've seen this so many times. And then onto the ugly, which is stuff which I like to think isn't particularly my fault, but when you're developing a fuzzer, you're going to have to develop around issues with the target you're fuzzing, because it's not on them to fix it. And the example is the big EBPF lock. EBPF verify has a big lock around it. And honestly, valid. How many people want to parallelize verifying 20 different programs? The answer is like no one, except me. So it's fun for me because I have to work around this. So one of the other fuzzers I looked at just moves the verifier into user land to allow it to parallelize, because then you can spawn it as a user process however many times. And to me this seemed ideal, but it seemed like a lot of effort, and if you change the behavior of the user of the verifier when moving it into user land, it seemed like a nightmare. Like, what if your user land verifier rejects it, but the kernel one does, so then you're missing out on genuinely good inputs? Or if the user land verifier accepts it, but the kernel one rejects it, you need to figure out where you've messed up. So it seemed kind of nasty to me, but they got it to work. So yeah, fuzzer executes in QEMU, because we need to virtualize the kernel environment. So I'm like, well, you know, I can't parallelize this inside one kernel, so I'll just spawn a bunch of kernels. So I just spawned a QEMU instance per hardware thread. And you now have the overhead of multiple QEMUs, but most of that is just time spent booting up, which is insignificant in the long run. And the other thing, which is I think a sort of theoretical downside, is that coverage isn't centralized. So two VMs might both get the same bit of coverage and then both treat it as new and attempt to fuzz it. This isn't necessarily a bad thing. Maybe one of them finds something and the other doesn't. But at the very least, if we're inside just one kernel, the coverage is centralized. So like only, I guess, one thread is ever working on a new bit of coverage. But because I haven't done it both ways, I can't confidently state if this is that big a downside. Next, EBPF can just be like really slow. First time I thought I had a bug, it was because the kernel stored for like 5+ minutes on a system call. I walked to like my dad, I'm like, hey, just found a kernel bug. No, yeah, I was wrong. Verify was just really slow. It will verify up to 1 million instructions. When you look at the kernel source code, there's a comment next to it just saying yes 1 million, which I find funny. I reduced that to 10,000 and also tinkered with a few other things. Because to me, like, if a program isn't accepted by 10,000 like loops or like iterations, it's probably not going to be accepted by 1 million. But I technically am now rejecting some valid programs. The issue of the speed of the verifier improved significantly, but it's still a relevant headache. But yeah, I will be saying don't be afraid to modify your target if like the benefits are like pretty notable. And then lastly, source code and choosing to read it. This is something I always think about when designing fuzzers and stuff. Ensure about like the best ratio of time spent reading source code to design a solution versus being gung-ho about it. So basically, the more time you spend reading about source code, you get an overview of sort of the larger design, and that's something that I do think is important. But I do worry about sort of mentally sort of putting too much trust in it and sort of thinking about all these checks and being like, oh, I'll need to incorporate that in my fuzzer to not get tripped up on them. To which you might over-sanitize your inputs. Like maybe that is like a weird edge case to bypass it. And yeah, some things is I really wish I modeled like control flow and thought about handling infinite loops more. So like my takeaway is like read the source code or analyze the like binary if you don't have that enough to understand the sort of big level features that you are going to need to incorporate your design around, but don't get caught up in the little details because it's not worth it. I will say it's not always a clean separation between the two though. Alright, pretty much near the end of the talk, just quickly talking about the actual bugs. The details, I found 5. 2 issues with casting, type casting, 2 issues with control flow, one of which is an infinite loop and one of which kind of lets you escape, and 1 issue with division instructions. I'm waiting on some of these to be patched, and that means I think my fuzzer can totally find more, but because there aren't that many bugs, once I find 1 bug, my fuzzer just keeps finding the same bug. So I'm just sort of chilling here until the kernel people do their stuff. And 2 brackets to 4-ish were exploitable, depending on how optimistic you are. And I'll just quickly talk about some. This one's been patched, so I can fully talk about it. When the verifier is doing its verifying thing, it tracks estimations about register values at all times for safety. What that looks like is if we are accessing an array of 5 elements, it will ask, is our max value for whatever we're using to index 4? Because if it's not, we can do out of bounds stuff. Now, there was an issue when casting to signed 8. They mishandled the var off part of their value tracking. You don't need to know what that is. But yeah, it didn't handle sign extensions properly. And so if we had a completely unknown value x, the cast of it, signed 8x, had an assumed max value of OX7F. That's not right. You can have OX80 and OXFF. And so this is fully exploitable. These are the types of bugs you really want from the verifier because misassumptions about values allow you to craft out-of-bounds stuff based on them. So you can assume if there's a program which has a safety property dependent on us having a max value of OX7F, but we actually had OXFF, we can get out-of-bounds stuff, and then we can escalate that to higher and higher privileges to code execution. So, as far as I can tell, like asterisks. The bug was born from code duplication because C is lovely and doesn't handle generics. The bug existed in the function coerce subreg to size sx, but not coerce reg to size sx. So that means ALU mov was buggy, but not ALU64 mov. And this to me screams, if you can, try and program abstractly and with generics. Because if you do so, you have to reason about logic at a higher level, and you get less messy bugs like this, where you're just copy and pasting, but you forget one line. Then the third bug was another issue with signed-unsigned casting for register value tracking. It was barely not exploitable to my best attempts, except I've now had new ideas and I've been talking, so maybe it is. And it exhibited similarly the traits you want about invalid assumptions on register values. Technically this isn't patched yet due to mailing list shenanigans, so I've anonymized it to not give you 0 days, even if I don't think it's a critical one. And it is of the form, and sorry for the lame thing, but once again don't want to give away stuff, U64 var equals U32 var equals S64 value. And the fixed version is like this. And the thing I found cool about this is like most of the bugs in retrospect, once you see the bug, you're like, oh, that's obvious. How did I not notice this? But this one, like, I don't think I would have gotten, because what's wrong is that there is an implicit U32 cast here. So S64 value assigns to the U32 var, obviously cast to U32, and then we're assigned to the U64 var, which has that U32 casting. So the top 32 bits of U64 are going to be 0 because it's going to 0 extend here because they're unsigned. So if S64 value has literally any bit set in the top 32 bit, there's going to be a disjunct here. So yeah, I found that cool. Just talking about those two bugs because they were the most interesting to me. And that's pretty much it. Thank you. Here's my website if you want my other ramblings or socials. Yeah.
Do we have any questions for Zach, our runner here? I will say we did have a Linux track option in the call for papers. A few people wanted it, but we only had one submission, which was Zach. So he's up here on the main stage. Here we go.
You said that your program didn't handle infinite loops at all. So what happens if it gets one? Does it just get stuck?
Good question. So, no, it basically just rejects it insofar as that it needs to, obviously we don't want to submit programs which can then sort of just store the kernel indefinitely. That's not something we want to do. If we allowed that and say like, you know, someone's using this in production and then someone accidentally triggers this and then someone's system is just stalled forever, that would just be cringe. So no, the verifier does some control flow analysis. It says I can't confidently declare that this isn't going to terminate, or if it can just clearly see it's an infinite loop, yeah, it will just reject your program and it won't get loaded into the verifier. One of my bugs was a control flow issue, which did then have an infinite loop. So that was one bug which they had to fix. Yeah.
Any other questions?
You mentioned syscaller earlier, which is pretty well known and run by in production by people who have a lot of resources to run fuzzing machines. Do you think there's any room for more EBPF fuzzing support in syscaller?
Yes. Ooh, hold on, let me 1 second. Oh, it's not projecting. That's totally valid. Oh, we're back. Yes, hold on. Simon, Scanl, EBPF, verifier. So basically, what I'm doing by this is I think one of the existing fuzzers is an extension of syscaller in which they have modified the syscaller grammars to do stuff. Let's see here. Control F syscaller. Okay, not this one. If I'm to be believed, I think someone's maybe attempted it, but I just don't think it's the best idea insofar as that, like, and I must admit, I'm not the most familiar with syscaller, but from what I looked, just having to use the syscaller grammar to model such complex inputs seems like it might not scale the best. So I think I don't know, I preferred leaning towards the sort of bespoke build it from the ground up. I think you definitely can have a go at it. I just think the development experience might be a bit like bad. But also like, I don't know, that's my view and assumptions, but like feel free to like prove me wrong and give stuff a go. Yeah.
Any other questions up there? Oh, there's one up the back.
So I seriously thought this one did EBPF.
Got plenty of time for questions.
Yeah.
Great talk, thank you. Did you ever consider writing an intermediate language to make modeling some things like control flow a bit easier and then lifting it to the EBPF bytecode?
Yes, I very much did. This was one of the things in which, when going into developing it, I was just like, oh, I'll just like directly work with the assembly. Like, how much can an IR benefit? Because it's such a simple thing to work with. But as I came across those issues, yeah. So I guess I think control flow would definitely benefit from it. I went with the sort of control flow graph and haven't pondered too closely how I would try and tackle, say, infinite loops. The other thing is working with the eBPF helper functions does increase the complexity of the type system by a good degree. One of which, an example I was thinking of is, and if I can find it, which I might not be able to, but the type system technically has this thing called pointer or null, in which some operations will give you a pointer, but you don't know if it's not a null pointer. So eBPF makes you work with, like, unwrap that by checking if it's null before unwrapping to a pointer. And that seems like something to me where I would really like to have an IR to then model unwrapping a pointer or null is a single operation, like in IR, which then unwraps to like several assembly instructions. So yeah, there's definitely value in there, and I think I would enjoy doing that, but I think it would be a lot of work, and I think in the end it would work better, but I can probably scrape by most of the improvements I want to do with my current solution. So yeah, I think, yeah, there's definitely merit to it, but I didn't initially see the merit, so I sort of just went this way. Yeah.
Awesome. Any other questions out there? Nope. Okay. Let's give Zach another big round of applause.